last video we made about scandium, we had no scandium sample at all. Then we were sent a tiny sample, and now we've been sent more than 80 grams of scandium by
80 grams, huh?
friend Anthony Lippmann.
Friend.
So
sure.
We can really give scandium a proper go.
Yeah, go. Meanwhile,
the reactions are quite nice.
Nice.
We've seen scandium burning for the first time. We've proved it's pretty hard to set fire to it.
Right.
There's a new demonstration.
A new demonstration, huh?
Which I thought was really good.
Yeah. How about this one?
Is famous because it is one of the elements that Mendeleev predicted should exist,
huh?
And he predicted some of the properties before it had actually been discovered. Scandium is relatively expensive so extracting those low levels out of different minerals is expensive. I've never seen so much scandium before, and I think it's quite unusual to have so much. The first experiment we tried was dissolving scandium in an acid, hydrochloric acid, and the reaction goes rather well. You put the metal in the acid, and it bubbles with hydrogen and water. And you will have the usual time of setting fire to hydrogen. But the liquid electric world was pretty messy. Neil filtered the solution, and it came out that we still a bit frozen, so I suggested adding a bit more acid. Nothing happened for a minute or two, and while we were arguing what to do next, nothing got through. So the first solution was a solution of scandium clear. So we then decided to add some potassium hydroxide to precipitate the hydroxide of scandium. As the dot of potassium hydroxide solution went in, we were neutralizing any excess of hydrochloric acid.
Sure.
And then forming hydroxide of scandium.
And then stop. And then, I don't know. What are we going to do with that, huh? I guess. This one? This one? This one? This one? So many to choose from. Oh, that one is cool. Play. Scandium, particle.
So you see it's slightly gelatinous, jelly-like precipitate forming. That's scandium hydroxide. We began with scandium metal, and this is the hydroxide salt of scandium 3+ and hydroxide OH-.
I know.
If you read descriptions about scandium on the internet, it says it burns very easily. So Neil took quite a big chunk of scandium and heated it in a Bunsen burner and got it really red hot. It didn't burn. If he squirted a bit of oxygen into it using a steel tube that had fired the oxygen into the flame, he did once manage to get it to light.
Oh.
And then it burnt really quite well.
Well.
And left a sort of thin whisker of possibly scandium, possibly the oxide, and Brady photographed it
Yeah.
lying on the floor of the fume
Floor.
cupboard. Undeterred by this rather bad burning, Neil then decided to try and make his favourite filings of the matter and see what that would do on burning. But before I tell you the result, let me tell you about my experiment with bromine. While I was reading about scandium, I noticed that the density of scandium metal was just below 3 grams per cubic centimetre, whereas the density of bromine is just above 3 grams per cubic centimetre. So I thought we could show how light scandium was by floating it on bromine. But I warned Neil before he tried it to cool the bromine with ice. Because you remember, bromine vapor is very dark red.
Yeah.
And I felt that if the bromine was at room temperature, then maybe clouds of bromine vapor so you couldn't see the surface. And also, if you cool it down, the density would be a tiny bit higher.
I know.
Anyway, they put the scandium in and it floated beautifully. But Brady was looking forward to a spectacular reaction, and nothing happened. And I was thrilled because we had demonstrated that scandium was light, and if it had reacted straight away, people wouldn't have believed that. However, when Neil took the scandium out of the bromine and put it into some water just to clean it up, then there was some sort of reaction with the bromine that was still sticking to the surface, probably because the water was reacting with the bromine to make hypobromic acid, HBr, which would easily react with the scandium. And at the end, the sample of scandium looked really quite dark. We're not sure why, but I think maybe that it had a coating of scandium bromide, or perhaps scandium tribromide, which one might expect to be a sort of dark reddish color. Scandium was discovered in Sweden by the Swedish chemist Nielsen, and he reported making a small amount of the oxide, but he was sufficiently convinced that it was a new element that he called scandium after Scandinavia. But what he didn't realise was that this was one of the elements that had been predicted by Mendeleev, and it took one of his colleagues, also from Sweden, Kleber, who published the paper really quite a short time afterwards, in which he explained that this element was the one that was predicted by Mendeleev. Part of the problem may have been that Nielsen, when he measured the atomic weight, got it not quite right, and Kleber got it much closer to the 44, which had been predicted. And very nicely, at the end of Kleber's paper, he publishes 2 columns, one with the predicted properties of beta-boron, as Mendeleev called it, and the other one with the properties of scandium, and showed how they matched up. There wasn't perfect agreement, but it was pretty good. And it was this prediction, was the success of this prediction of Mendeleev, that made people begin to believe really strongly in the value of periodic tables.
So I've got a whole bunch of things that relate to scandium. I guess firstly, this is the rock that we probably get most of our scandium from. It's ore of aluminium, we tend to call bauxite. It's actually made of a whole bunch of other minerals, but the rock type we call it is a bauxite. So that's where we get scandium from, but it's only trace. There's only a tiny amount of scandium in there. We process it for aluminium and we get a tiny little bit of scandium out. So that's quite important to realise. But there are a few minerals that exist where scandium is a really significant component of the actual mineral. There's maybe about 20, not so, and we've got 6,000 minerals in total across the globe, so 20 is a really small number. But again, in the collection here, we're lucky enough to have some examples of those. And one of them is this mineral here called HoPE, and it's this great dark green dark crystal. And it's a scandium silicate, so it's got quite a lot of scandium in it.
What's it attached to there?
It's attached to a feldspar, so which is one of the really common minerals on the planet. Most of the time you find feldspar, you won't find any scandium, which is a really unusual occurrence. So there's another one, little one. And you'll see there's a change in colour on this crystal. So it's dark at one side, a little bit lighter at the top end there. That could be just because the different elements and slightly different trace elements of this crystal growing so that's actually changing colour. But yeah, they're all scandium which is really pretty exciting. We don't have any other really rich scandium bearing minerals, but there are a couple. Like this is a really rare example. This is one called basite. The basite is actually tiny little blue crystals, so tiny that you're not going to be able to see them on this. But it's a nice representation of how rare scandium is.
So the bulk of what you're holding there and all that stuff I can see, that's not the basite, that's not the
Basite, no, that's really disappointing. You won't be able to get close enough to see the basite. It's tiny, tiny little blue crystals. But basite's the scandium equivalent of a much more well-known mineral that it's called beryl, which produces the gemstone aquamarine. So this is a lovely specimen of beryl. There's no scandium in this. This is a beryllium aluminium silicate. But what happens in basite is that the scandium substitutes for the aluminium, so you get a beryllium scandium silicate, and so we call it a different name for the different elements that is dominating the structure.
So Mark, is there somewhere on Earth or some planet somewhere in the universe I could go where there would be a cave full of beautiful crystals like that scandium's doing as well?
I have no idea. If there is, we haven't found it yet. Scandium it doesn't concentrate very much. There's very few places on the globe where we get scandium all together and enough of it to form big crystals. I mean, these HoPE, these are sort of, there's a couple of other museums that have slightly bigger crystals, but some of these are the biggest concentration of scandium within one mineral that there are. So it's a pretty rare thing.
As you know, Neil likes to produce filings of elements. So he filed away at one of the pieces of scandium. To begin with, he held the piece in his hand, but then decided to use a vice so he could attack it more systematically. And he got a reasonable pot of filings, which he then sprinkled into Bunsen flour. And unlike the lump of scandium, the small filings felt really well. In fact, eventually, he tipped a whole lot into the Bunsen, and it produced so much light that all Brady's cameras were completely washed out by the intensity of the light. It's quite reasonable to ask, why did the little filings burn so much better than the larger lump? There are two reasons. One of them is because if you think of a tiny piece, the surface area is very much larger compared to its volume than with a large lump. So that when it starts reacting with oxygen, the amount of heat that is produced by the reaction is large compared to the amount of heat needed to heat up the lump of metal. So if you've got a big lump, there's much less surface area, and so it's much harder to heat the metal up to get a self-sustaining flame. And if you add a bit of oxygen, then you're helping the reaction go, but it's still touch and go whether you will get enough heat to make it self-sustaining. The other point is that if you have smaller pieces, they can heat up much more quickly in the flame, and again you will get the reaction to go better. So this demonstrates how chemistry depends not only on the actual reaction, but it can also depend on the physical form of what it is that's reacting. And if you have a finely divided powder, reactions often go much better.
Hey everyone, if you're a bright, curious, clever person, and you're right at the start of your career, particularly maybe looking at internships, then James Street is a place you should check out. If you haven't heard of James Street, they're a quantitative trading firm with offices all around the world. They're at the cutting edge of things like machine learning, distributed systems, programmable hardware, statistics, and James Street are currently taking applications for internships in quantitative trading, software engineering, research, and plenty more areas. It's pretty broad. The summer internships are in New York, London, and Hong Kong. You'll do amazing work, meet fascinating people, and the internship program also includes cool social events, guest speakers, all hosted in their world-class high-tech offices. I've been to some of them, they're very cool places to work. In addition to a salary for the summer, James Street will also cover all your flights and accommodation. It's an amazing opportunity. Last year's interns came from 22 different countries and all sorts of backgrounds. You don't need to know about finance, they just want people who are curious, collaborative, the sorts of people who I imagine might be watching these videos. For more information, check out the link in the video description down in the comments under the video. I'll put everything there.
And then with the match on the stick, it went with a big bang. Like a mirror for a magnet. So if you put a magnet just above it,
Yeah. How about it?
today we're going to talk about tungsten. We spent a long time.
Yeah. And maybe we will talk about ourselves and the universe. I see you. Bye bye.